Gravity pulls things down at an acceleration of 9.8 meters per second squared. But compare that to electromagnetism. A tiny magnet pulls a paperclip up instantly because electromagnetism is 10 to the 36th power stronger than gravity. Consider that a small magnet is successfully fighting the pull of the entire planet. This is the weakness problem. Einstein showed us that gravity is actually the curvature of spacetime. When mass is present, the geometry of the universe warps. In his field equations, the metric tensor represents this geometric fabric. Gravity is the stage itself, not a particle we can simply pick up. With electromagnetism, we have a control dial. Flip a switch on a circuit, and a magnetic field appears. But there is no local switch for gravity. A generator does not just turn on. To detect it accurately, we use atomic interferometers. By dropping atoms and tracking their wave patterns, we reach a precision of 10 to the negative 12th G. This sensitivity is like a scale that can detect the weight of a mountain shifting because of a single grain of sand. To create anti-gravity, we would need to warp space in the opposite direction, using negative energy density. This requires exotic matter, which is purely theoretical and currently impossible to generate. We face a massive scaling gap because spacetime is a global property, while our tools are local and tiny. Remember these 3 points. Gravity is incredibly weak, it has no local particles, and it is fundamentally geometrical. We see this geometry in gravitational waves, which are ripples moving through the fabric of space. The fundamental challenge is the scale. Now, let us step inside the lab as we transition to the world of anti-gravity research. Picking up from the profound challenge of manipulating space-time curvature, we see that the solution isn't a single device, but a globally distributed research architecture. This multi-layered approach serves as our essential infrastructure of discovery, allowing us to attack the problem from every possible angle. We begin with high-energy particle colliders. These massive machines probe interactions at the tiny 10 to the negative 15 meter scale. They search for gravitons, or supersymmetric partners, that might reveal how gravity integrates with other fundamental forces. Next, we look at the Casimir rig. These experimental setups investigate the quantum vacuum. By placing plates mere nanometers apart, they attempt to manifest negative energy densities, which serve as the theoretical fuel for many anti-gravity concepts. Then we have atomic interferometers. These are our eyes, using the wave nature of atoms to measure background field fluctuations as small as 10 to the negative 12th G. These precise instruments allow us to map the tiniest changes in the gravitational field across the experimental space. To make sense of this massive influx of information, we need a centralized engine. These advanced AI-driven scientific computing clusters serve as the backbone, running high-fidelity simulations of field interactions that are simply too complex for traditional physics. When a collider detects a subtle anomaly in particle decay, the signal travels to the compute cluster. Here, AI models compare the raw data against trillion particle simulations to see if a new physics signature has emerged. At the same time, the interferometers verify if those particle-level anomalies actually manifest as a measurable change in local gravity. This cross-verification ensures that every discovery is backed by multiple lines of experimental evidence. This integrated search architecture represents a major shift in our approach. We are moving from the world of pure speculation into a new era of data-driven experimentation, using every tool in our arsenal. As we center our focus on this unified framework, we can see how particle physics, quantum vacuum studies, and precision measurement all converge. This synergy is what will ultimately unlock the secrets of gravitational manipulation. With this powerful toolkit in place, what specific theoretical recipes are scientists currently cooking up to bend or break the rules of gravity? We will explore the most promising potential solutions in our next segment. Welcome to our exploration of pathways to gravitational manipulation. Here, we move beyond experimental architectures into the theoretical blueprints that might one day allow us to master gravity itself through a global research network. Our first path involves the generation of exotic matter. By using a Casimir setup with two parallel plates, we can restrict the types of vacuum fluctuations that can exist between them. Notice how fewer waves fit inside than outside. This difference creates a measurable pressure and a region of negative energy density relative to the surrounding vacuum. This negative energy is mathematically described by the Casimir equation and is a crucial ingredient for stabilizing more advanced gravitational structures. Next, we consider the warp field projector, an application of metric engineering known as the Alcubierre drive. Watch as the grid of space itself is manipulated. We expand space behind the craft and contract it in front. In this model, the ship remains stationary within its own local bubble of flat spacetime, while the metric itself carries the bubble forward. It is a way to move without technically moving through space. A third approach uses high energy density via a petawatt laser focused onto a vacuum target. By concentrating an immense photonic flux, reaching intensities of 10 to the 14th watts per square centimeter, we can directly influence the stress energy tensor. As Einstein's field equations show, any massive concentration of energy must curve the local geometry of spacetime, potentially allowing us to create gravitational effects using raw power rather than exotic materials. When we look at these three systems side by side, we see three very different strategies for the same goal. Negative energy density through the Casimir effect offers a known physical phenomenon, but scaling it up for propulsion requires materials we can barely conceive of. Metric engineering via warp fields provides an elegant mathematical solution, yet it demands energy levels that currently exceed our total planetary output. High energy density lasers leverage our growing mastery of optics, but the precision required to shape a specific gravitational field is still beyond our reach. Each path presents its own unique hurdles in energy cost and material availability. These ambitious concepts represent the current frontier of theoretical physics. As we refine our blueprints and engineering capabilities, we must ask, which of these pathways offers the most pragmatic starting point for our first steps into gravitational control? We are now witnessing a profound shift in how we approach gravity. Rather than relying solely on abstract mathematical models, researchers are moving into the laboratory to focus on incremental and observable physical phenomena. This starts with extreme environments. Using high-powered magnet arrays cooled to nearly absolute zero by cryocoolers, we can generate magnetic fields exceeding 20 Tesla. This energy is channeled into a vacuum chamber, creating the perfect conditions for quantum exploration. Inside this chamber, we use atomic interferometers and gradiometers to monitor for the smallest space-time distortions. By manipulating quantum fields within this localized area, we are attempting to interact with the very fabric of gravity in ways previously thought impossible. The atomic interferometer is a critical piece of the puzzle. It works by measuring incredibly precise phase shifts in matter waves, allowing scientists to see if the gravitational field has been modified, even by a tiny fraction. Simultaneously, we look to high-energy physics. Particle colliders and advanced detectors search for new fundamental particles or interactions that might bridge the gap between quantum mechanics and general relativity through intense particle flux. All this information flows into an AI computing cluster. These systems are designed to process massive data sets from both the gravity experiments and the particle detectors, searching for subtle anomalies or patterns that a human researcher might overlook during the noise of an experiment. When the magnets are engaged, the atomic sensors begin reporting data. We look for a continuous flow of information where results from the vacuum chamber and the particle detectors align, moving us closer to a confirmed discovery. When these two independent data streams produce a matching result, we have a coincident signal. This is the gold standard of experimental physics, suggesting that we have truly observed a new gravitational effect. However, the real world is messy. External vibrations and seismic noise can easily disrupt these delicate measurements, masking the signals we are trying to find. The entire experimental setup must be incredibly stable, but even then, environmental factors can overwhelm our instruments and hide the very evidence we are looking for. This is where the AI cluster becomes essential once more. By sending filtering instructions back to the instruments, the system can mathematically subtract the background noise, isolating the true signal from the chaos and allowing the experiment to proceed with much higher precision. By combining extreme magnetic fields, cryogenics, quantum sensing, and particle physics with advanced machine learning, we are building a robust architecture for discovery. This integrated approach is no longer just a theoretical dream. It represents our most promising path forward, slowly laying the foundational knowledge required to one day master the forces of gravity. Every data point brings us closer to a future where gravity is something we can finally engineer. While superconducting pathways represent our best modern effort to manipulate fields, the true cost of gravity manipulation is staggering. To visualize this, compare the small circle of our current global energy generation to the massive circle required for a functional warp drive. We are talking about 10 to the 44th joules, which is roughly equivalent to the entire mass energy of a planet. This leads us to our first constraint, the energy gap. Theoretical models for gravity control often rely on negative energy density. In physics, we usually treat the vacuum state as the 0 point. Creating stable negative energy, shown here below that baseline, might actually violate fundamental energy conditions and lead to catastrophic instability. Our second hurdle is environmental noise. The signals we need to detect or generate are incredibly tiny, around 10 to the negative 12th G. This signal is easily drowned out by a chaotic sea of seismic and thermal noise. While atomic interferometers push the boundaries of precision, we face a paradox. Measuring gravity requires extreme isolation, but gravity itself cannot be shielded. Perhaps the deepest challenge is the unified field problem. On one side, we have quantum mechanics describing the discrete world of particles. On the other, general relativity explains the smooth, continuous fabric of spacetime. A massive gap exists between them at the Planck scale. When we try to combine the wave function of quantum states with the field equations of relativity, the math simply does not resolve. When we summarize these limits, the scale of the challenge becomes clear. We face an energy shortfall of 30 orders of magnitude, a noise floor that hides subatomic signals, and the lack of a complete theory of quantum gravity. Ultimately, achieving anti-gravity is not just an engineering problem to be solved. It is the final exam of modern physics.